Let me begin by thanking Kostya, Uriel, and Rahul for inviting me to this meeting. I'll also being the local speaker from ICTS, I sort of extend Rajesh's welcome to all of you, and hopefully we'll have you on campus soon enough. Uh, what I'm going to talk about is an area that I've been sort of interested in, thanks to friends and colleagues who work on this much more than I do. And I should preempt by saying that this talk will not have real turbulence in the sense Takeshi and Joyento were describing it in the last couple of days, but I hope there's enough sort of structure in the work that's being done, which might be interesting. And also, chaos has a long history, so hopefully there's something new for all of us to look at. Also, since the organizers asked us to have a certain pedagogical content to it, so I'll begin with a little background of of how I got drawn into this problem, and that context comes really far from turbulence or things that we do. So this is an area where I don't work, but I think the genesis of the problem really is from here, thanks to colleagues and friends at lunch. So in the last sort of few years, and there are references, I apologize in advance that some of probably I'm missing out on relevant references, but these are the ones that I have been exposed to. So in the last few years, there has been a lot of work, especially amongst the high energy physicists, string theorists, etc., in trying to understand quantum chaos through the prism of the butterfly effect, the classical butterfly effect, something that we have been people like most of us here in the audience have familiarity with, and Martin gave a talk on the Lorentz system yesterday. So very briefly, what they were looking, the problem that they were looking at, Maldacena, Stanford, etc., was the following. So if you consider Hermitian operators V and W, then the question is really, what is the effect on W of a perturbation on V? So essentially, you want to calculate this function f of t, which is the square of the commutator between V and W. You take an ensemble beta as the inverse temperature. And what they sort of not surprisingly show that for chaotic systems, this object can become large. And in particular, this object is characterized by a Lyapunov exponent, lambda. I mean, you have a spectrum, but let's talk about the largest Lyapunov, a butterfly velocity VB. And the whole point that these people have been looking at, and again, the reference list is really incomplete, is to try and sort of understand the growth and spread of perturbations in a quantum many-body system. And there are several applications, which I, of course, neither an expert nor do I understand very well, which are in the areas of information scrambling, extremal black holes, etc. So, a certain consensus has emerged, and because, geographically where I work with a lot of my close friends in this business, and because of conferences like the one we are having, so a sort of consensus that I get amongst friends and colleagues is that these objects, these so-called out-of-time ordered commutators, the f of t that we have written up there, are really the diagnostics of quantum chaos. So one of the sort of, takeaway message from this is this bound on chaos, which was proposed by Maldacena, Schenker, and Stanford, and I've highlighted here, which is that the largest Lyapunov is essentially bounded by the temperature. And, there is a certain heuristic way to sort of see it. I think it's not incorrect, is in terms of, for example, energy time uncertainty principles, etc. So having sort of heard these things a lot, many of us were curious is, how for classical systems, how could one start thinking about such bounds? Are they even well defined? How do we adapt tools developed there. And I'll come back to this question a little later, why, this problem, it's an old problem, but why, there's some recent interest in this. Essentially, what's the classical analog of such OTOCs, all right? So essentially, what we want to go is from the space of commutators, from the world of commutators to Poisson brackets. And a couple of years ago, with several colleagues at ICTS, students, etc., you see the whole list there, and a couple of our friends and collaborators elsewhere, David Hughes and Roderick Moisner, we sort of generalized this idea for a classical spin system. So you probably already see where I'm going. So we've gone from the quantum world to a classical spin system to try and see how we can generalize these ideas. In particular, the model that we had looked at was the classical Heisenberg spin chain at infinite temperature. So essentially, nearest neighbor ferromagnets, there's the Hamiltonian, and the dynamics, the spin precession dynamics is well defined. So essentially, you're living on a ring at high temperature, so all the spins are pointing in various ways. You sort of constrain the norm of each spin to be 1. Why is this an interesting problem? The interesting problem is, as we all know, if you're looking at the 2-point dynamical spin correlator, and this thing will come up later when we come to hydrodynamics, so it's something that we can keep in mind, is essentially the 2-point dynamical spin correlator is diffusive. All right, so I mean, here's a plot from the paper, which essentially shows, and you have the formula, that there is diffusive spreading. There's nothing ballistic about it. However, if we want to adapt those ideas, so let us see if we can get a measure of where certain spread or ballisticity in the spread of perturbations comes in these systems. So again, this is not really the bulk of the talk, but it's just to motivate why I'm doing what I'm doing for the bulk of the talk. So the strategy that we use, and you'll see a familiarity in when we come to hydrodynamics, it was essentially we generated a random spin configuration, infinite temperature Gibbs ensemble. So that's copy A of the system, and we make a second copy of this with a little perturbation on one spin. Let's assume that that spin is at the origin, all right? And we sort of just rotate that spin by an epsilon amount. And then what we are going to do is essentially evolve these two systems independently and try and measure how fast they decorrelate. That's the idea. And what one is able to show, I mean, here there's the sort of more precise result where one can sort of take the right traces, etc., to come to the classical limit. But essentially, when the dust settles, all that we are measuring is this decorrelator, I think christened by my good friend Shubro, which is essentially 1 minus the spin-spin correlator of the two chains, which is the same. The second expression is just an identity of the first. So essentially, this decorrelator, when spins are perfectly correlated, which is when you've just perturbed it infinitesimally at one point and you evolve at early times, the two chains are perfectly correlated. So the decorrelator will have a value of 0. And then slowly as you evolve in time, they become decorrelated, and d of x comma t will eventually go to 1. So here's really the sort of central message of this work. And this was this beautiful light cone that we saw. So what we were plotting was essentially the decorrelated d of dxt on an xt diagram. And inside this light cone, the red, the decorrelator is order 1. So things are, from the expression, you see that inside this, the two chains have completely decorrelated. Outside this light cone, they're still correlated. So as you can see, T is on the vertical axis, so the perturbation takes time to spread. And the point is that you get this rather beautiful light cone, which allows you to sort of define in some sense the butterfly velocity, in a Lieb-Robinson sense. And one could sort of continue this game and make it more rigorous, which I'm happy to talk about later, and essentially measure the decorrelator. And what we were able to see was, and this is not really new. I mean, there were earlier work by Lyapunov polity, including probably some people in the audience here, where what one sees is essentially a velocity-dependent Lyapunov exponent. And to that sense, this work sort of, connects with earlier results for other sort of systems. So in summary, what we really found was that there was an exponential growth and ballistic spread of an initially localized perturbation, and it was characterized by a certain, Lyapunov exponent butterfly speed. What was rather nice was the fact that the spread of this wavefront, if you notice this d of x comma t for different time, there's a wavefront of this perturbation which is moving. What was rather nice was that one was able to connect how this wavefront propagates to the classical Kardar-Parisi-Zhang equations. So there are other examples of this where 2-point correlations are diffusive, but there's a ballistic spread of perturbations, and I've listed a few that I'm familiar with. So these examples are here for those of you who are sort of interested in etc. So the question really comes, and this question, to be honest, of course, I'm trying to bulldoze my way and sort of argue that we should bother, but there are, also doubts in my head. So that's the purpose of giving this talk to get certain feedbacks. So why are we bothered about these classical analogues? So part of it is to understand the nature of intrinsic differences or universality between classical and quantum many-body chaos. The sort of Maldacena-Schenker-Stanford bounds of temperature, you can get it through the uncertainty principle. You don't sort of necessarily have that sort of tool in the classical problem. More importantly, a lot of our colleagues have been trying to find connections between thermodynamic variables with the timescales of the chaos, connections between chaos and transport in strongly correlated systems. For example, can we cook up, let's say, diffusion constants in terms of lambda and VB? Dimensionally, we can. The question is, how do we go about sort of rigorously showing it? A broader sort of grand goal, and I'm not even pretending that I'll have an answer to that, is sort of to find a unified mechanism which must be at the heart of thermalization, ergodicity, equilibration. The sort of standard pillars on which classical statistical physics rests, and that's sort of interconnected with significance of chaotic length and timescales in the dynamics. And most importantly, is this a way to capture ballistic spread when 2-point functions are diffuse? And you'll see we'll come back to this question within the model that we do. So in this context, before I move into more comfortable territory, I should also flag recent studies. Again, this list is with a view to highlighting work of friends and colleagues, not necessarily an exhaustive list. And a lot of my friends and colleagues have actually looked at this in the last couple of years. So, Shubro for spin liquids, for Duffing chain. A very interesting paper is by Jeremy, Alexei, and Simon, who are in the audience, where they've looked at, shear flows and essentially sort of seen a certain interesting transition between the butterfly effect and spontaneous stochasticity. I think there are talks on spontaneous stochasticity in this meeting. And also, a very interesting work by Shumilon and a student Shibram is in the 2D anisotropic XXZ model, where they actually look at the behavior of this chaotic behavior across the Kosterlitz-Thouless transition. And so, what I'm trying to get at is, for right or wrong reasons, there is some sort of, collective cooperative phenomena in trying to understand all these questions which bother some of us. So working in turbulence, the natural question for me is, can we adapt these ideas, or at least, try to look at the quantum bound of the Lyapunov exponent within the framework of equations of hydrodynamics? That's because so far, if you've looked at those examples, and I haven't been coy about it, in real partial differential equations in systems which are sort of naturally chaotic, this question has not really been, in this language, in this sort of prism, being explored. So the temptation really is to put these ideas to test in the most natural and well-known example of chaotic systems, namely turbulent flows, something that I'm somewhat familiar with. The problem there is that all the tools that I have picked up from friends and colleagues are in a framework which has a certain Hamiltonian structure or a statistical description, an equilibria description, thermodynamic variables well defined. Whereas in the classical world of turbulence, we are looking at driven dissipative systems. So that's the problem. But given that there is this temptation, one looks for redemption, of course, and what one what one is looking for is some variation, which while being nonlinear and chaotic, still retains enough of the Hamiltonian structure, in particular energy conservation, which allows us to sort of define a statistical equilibria. All right, so that's the background that we are coming from. So I know that Marc Brachet will speak a lot about thermalized fluid. He's one of the sort of, godfathers of this. But let me sort of, for the purpose of this talk for self-consistency, just talk a little bit about it. So one ideal model that we could think of, which sort of satisfies this criterion while still allowing us to look at the classical OTOC problem, are what I'm calling thermalized fluids. Essentially, these are inviscid three-dimensional or one-dimensional Burger's equation with a finite number of Fourier modes through Galerkin truncation. So essentially, we take the inviscid Burgers and the 3D Euler. There was, in the informal discussions yesterday, there was a lot of discussion about, weak solutions, dissipative solutions, even when viscosity is 0. So what we do is essentially, and we are working with periodic boundary conditions, so we have a well-defined Fourier basis. What we do is introduce a finite truncation wave number, kg, make it finite dimensional with a finite number of modes, ng, and essentially get the Galerkin truncated inviscid equations. So what we do know from a lot of work, and I'll flash some of them just to give credit to people who've worked on this, is that solutions of these are chaotic, thermalized solution. They thermalize within a finite time. Essentially, it allows me to have a well-defined statistical equilibria in terms of energy equipartition, in terms of Gibbs distribution, most importantly, in terms of being allowed to define temperature through those distributions, all right? So this is not something new, the notion of thermalized fluid. So here are some nice references, Andy Maeda, Marc Brachet and others who've sort of looked at it. Actually, it goes back to Lee and Hoff and then Kreitlin and others who've also looked at this. Also in our group, we've done quite a bit of work on this. So just to give you a sense of what happens, so this is in real space. So if you look at 1D Burgers or 3D Euler, of course, the chair of this session has also worked on this problem. You end up getting thermalized solutions as opposed to what I show in black, the so-called entropy solution, which Edries and Claude and others have discussed. What's really interesting, and this is really work in progress, is how to understand the analog of these oscillations or what kicks in thermalization for 3D Euler. So you see these oscillations in our 3D Euler field, which are very similar. And so my student Sugan is working on this, and hopefully we'll have some understanding. So that's how these fields thermalize, and we are looking really at taking the fields when they're thermalized. So the good thing is, if you measure the distribution or the PDF of these velocities, they're essentially Gibbsian. And the great advantage of this for what we are about to do is that you can vary the temperature trivially. And this is true, also in the theory that I'm going to discuss, by just varying the amplitude of the initial condition since energy is conserved. All right, so in 3D Euler Burgers, I'll sort of flash them side by side. This work is on both. You do see that. And also you see the energy equipartition. So in red is the energy equipartition, d-1, so k to the power 0 and 1d, as opposed to this nice k-2 scaling that you would have for the entropy solution, which has shocks and whatnot. Similarly in 3D, so I love this sort of spectral plot from Mark's paper a lot. So I'm not putting in my data, except in the little inset to show that if Mark had waited long enough, he would eventually find a completely thermalized spectrum which goes as k squared. But this is essentially what Mark pointed out in 2005. Okay, so that's the system that we are looking at. And that's going to be our sort of playground. So in this sort of thermalized fluid, we want to understand many-body chaos in a way that, you know, I'll define precisely as we go along. But before that, you know, by we, what I really mean is my student Sugan, who will finish his PhD in a year or so. Dheeraj was a former student who is now in Paris doing his PhD. And Shubro, a colleague and friend, and you know, at ICTS. And Shubro is really one of those who sort of pioneered this field in the last few years, and you'll see references to his work, and you know, most of the stuff I've learned is from him. All right, so how do we go about playing this game? So let me begin with the burgers, because that's slightly simpler. So we take the Galerkin truncated burgers, we use spectral methods, I'm not going to describe them. We evolve it, we wait till it thermalizes, you have a statistical equilibria, nice Gibbs measure, we do it for various temperatures in the way that I've discussed. And now we do the following strategy, exactly like in the Heisenberg problem. We take the thermalized solution, we make a copy. We call that VA. We make another copy, and this time I'm going to perturb it in Fourier space by just adding a little perturbation at some wave number Kp. All right? And then I independently evolve these systems. And as I evolve, I monitor this decorrelator, essentially the difference square between the two chains. I'm going to try and see how this decorrelator behaves. Theoretically, in the burgers, this problem is reasonable to address. I, of course, won't go through the algebra, and you know, I'm happy to discuss all this offline or later. But theoretically, one can sort of write down the equation of this decorrelator, essentially write down the Burger's equation for Vn and Vb and sort of take subtractions, blah, blah, blah. And this is the linear, and then you can linearize it. And essentially, theoretically, you come up with these two predictions. And what you do, and the prediction is that at short time, this will grow exponentially. At long times, this will saturate to the energy per mode. And that saturation happens just because at very long times, A and B loses memory of where it began with. And essentially, the two systems are completely decorrelated. So you can open the square of this, take the averages, and you're done. And much more interestingly, theoretically, what we end up is having a lambda, which is ng square root t, all right? And so again, I recall the quantum bound, which was linear in time. So what we are now, so let me sort of tell you a little bit about the results. I'll come to the lambda at the end once I've discussed the Euler issue. So what we find...
A question here, Samriddhi.
Yes, Itamar. Yes, please.
Isn't this trivial? Because you say you have... I mean, you have a thermalized system, so v squared, the velocity squared is of the order of t. So you just prescale by v, right? I mean, v...
Yeah, so, from the URMS velocity, right? You're thinking about... Yeah, sure. But I'll come to the slightly non-trivial part in a bit, huh?
Okay.
Yeah. I mean, as we'll see, because then the Euler heads, what we'll see is the ballistic spread of these perturbations, not just the growth.
Okay.
Yeah. So... all right. So what we really sort of see is that if you're okay. So where was I? Yeah. So we are looking at the decorrelator as a function of time, and what we essentially have is if you look at the linear system. So these lines are for the linearized solution; they grow forever. However, if you look at the full non-linearized model, you essentially need the nonlinearity to get this thing saturated, to have a cutoff how far things will grow exponentially, all right? So, I mean, again, not surprising, but, you know, one still needs to sort of show it in a slightly rigorous way, right? So that's essentially the Burger's case, where you can make, as Itamar pointed out, dimensional arguments, and essentially your time scale would go as 1 over u, would go as something like URMS length scale, right? And that sort of gives you square root t. But the question of what length scale do you pick up in a thermalized system becomes essential. And we'll see that that problem really becomes moot. All right. So what do we do in, so just, as a take-home message, this game is played in Fourier space. So we can, again, go back to the 3D Euler equation where we have, higher dimensional problem. We, again, solve the truncated Euler equation till things thermalize, till you have a nice Gibbs distribution. And here we adopt a different strategy. We make a copy, but here we make the perturbation in physical space. So what we do is we introduce a small perturbation, let's say at the center of our box. The perturbation is written in terms of the curl of a vector just to ensure that, the incompressibility is not destroyed. And it falls off very fast from this. So it's really a tiny perturbation with an amplitude epsilon 0. AI will control the temperature. We again independently evolve these two systems and we measure delta U, which is going to be how this perturbation spreads. So before I continue here, so let's look at just the raw data of how the perturbation spreads. So here's a movie that you can see. And you see this was the perturbation at the center. As time evolves, this perturbation grows. It has a very rough, as you can see, it has a very rough boundary, which, once you integrate over different R's, you can smoothen it out. And one is trying to understand if, one can actually understand this front propagation a little better, etc. But that essentially is visually how you would expect these perturbations to grow. And as you can see from the scale, the perturbation really grows. So from this, it's sort of easy to define a local decorrelator, phi RT. So essentially, you are on a ring of size R away from the point at which you introduce the perturbation. And you want to see what phi RT looks like. Or you can look at the global perturbation. So you integrate out R and you look at how phi of t evolves. All right. So for the Euler, the sort of theory is much more interesting. And there's something that sort of comes up, which certainly was surprising for me. So again, modulo the algebra. So from the 3D Euler equation, you can write down component-wise slightly easier. You can write down an equation for the evolution of this perturbation, delta U, with the appropriate Green's function to take care of the pressure terms, etc. And this equation, within suitable approximation, so the trick was, all the approximation one had to sort of what terms are not important, etc., had to be validated from numerical data. So essentially, you can come out with an equation for this global decorrelator phi t, which is essentially delta Uij, Sij, delta Uj, all right, where Sij is the standard stream rate tensor. So what Sugun was able to do was essentially to diagonalize this and solve it in the basis of these eigenvectors of the stream-Tane matrix. And what was rather surprising for us was the fact that these perturbations, and this was checked numerically, of course, because a lot of the ideas, assumptions are really not on, and we are still working on trying to make these assumptions more rigorous, was that these perturbations really align with the component, with the compressional direction. So when you do all of that, and when the dust settles, and if lambda c is the eigenvalue of that direction, you essentially find that phi depends on minus lambda ct phi. So recall that lambda c is a negative number. So again, and after that, again, heuristically, Itamar, you're right, just as you'd expect the quantum bound to be linear in temperature from energy uncertainty relationship kind of argument, Itamar. What you again have here is a more concrete, rigorous way from the equations that we, from the analysis from the Euler equation itself in terms of the strain rate tensor, etc., is a prediction, and let me just check the time, is the prediction that at short times you have an exponential growth, which grows fast, and at long times you have the saturation, this modal saturation, and the lambda again sort of follows the square root temperature. So I should have mentioned, which I ignored, but the reference luckily was there, that the square root T is something that, Kuchan had sort of predicted for classical systems in this paper, which, I mean, the reference I know is an archive, but, I'm happy to be updated, where for classical systems, using the energy manifold arguments, etc., he was able to sort of come up with this conjecture of square root temperature. All right. So how does the numerics bear out? So this is a plot of phi RT. So, these are at different values of R. So as you can see, this perturbation picks up at different times. So there is this ballistic spread, which has an interesting behavior with R, which I'm not going to talk about. I can talk about it offline for the simple reason that we are struggling theoretically to understand the exponent, how it spreads with R. It's not confirming to things that we would like to believe. And this dashed line is not a fit, but this is the solution of the linearized system that I talked about. So it really comes from this linearized equation, which Sugan had shown. So again here, the full nonlinear system shows this beautiful saturation. And that's the point, again, might be trivial to me. It became less and less obvious the more I sort of worked on this problem, how the nonlinearity sort of, enforces this saturation at a certain time scale, whereas just the linear system just explodes all the way as far as, we computed things. And if you look at the global thing where you average out things with R, you see the nice collapse. This is when you factor in the ballistic spread, etc. All right. So all of this sort of leads me to the sort of final, well, it's not really the final slide, I apologize, but it really leads me to the final sort of the punch line in some sense. And although from energy arguments, it might be intuitive, but, somewhere in the calculation, sometimes intuition breaks down and eventually you recover that intuition. So what one sees, and this is really combined data of the Lyapunov from our Euler and Berger simulations, and the straight line shows the square root T dependence. So what we've done is we've taken the Lyapunov and scaled out the degrees of freedom. So here you see, for the Bergers, I've listed out everything. For the Euler, it was too much to fill in the plot. But you see the real insensitivity to where I'm perturbing. If you factor out the perturbation strength, it scales out nicely theoretically, and it seems to sort of bear out numerically. So I'm happy to go to my grave with the validity of these numerical results. And the scaling is really nice. Huh? I mean, the reason, as you can see, is, so part of this we uploaded on archive because, Dheeraj had to also go to Paris, but we are fairly sure of our Berger's results. Still, we were hit on our, wrapped on our knuckles a little. And so we really moved into Euler, and right now we are brushing up the Euler results to sort of, so it's much of it is in preparation. All right. However, when you sort of look at this sort of result, the naive question, this part, again, heuristically, it's easy to understand. I should warn you that rigorously, we don't have a nice proof yet, is, I mean, these Lyapunov exponents should be connected with the decorrelation time, right? And what we looked at essentially was the autocorrelation function for the 3D Euler. Again, in the thermalized regime, unlike people working in the fully turbulent problem where things are much harder to do, here we are lucky. In the thermalized problem, we can sort of calculate this autocorrelation function and from there fish out the decorrelation time, right? So here's a plot of the autocorrelation function. You fit a nice Gaussian. So there is a slightly technical point here, and let me sort of, and I think this will interest people like Sergey and Mark certainly, and probably Uriel if he's listening, is the following, that if you calculate this autocorrelation function at a time when the spectrum is not fully thermalized, so you, let's say, have the really larger scale which have not been fully thermalized. It's a point that, you know, Marx stressed in his 2005 PRL. What you have is the autocorrelation function not going all the way to 0, right? So, quote unquote, permanence of large eddies, if you will. However, if you actually do it once things are fully thermalized, I show it in the inset, that's the sort of regime we are in, then you do see the autocorrelation go to 0. So this is really, you know, it's an interesting point. It was not something that I'd anticipated. And so, you know, probably I was stupid, but I thought I'll share this, with you. So you can fish out, so coming back to the story, so you can fish out this autocorrelation time, take the inverse time. So here, you know, I plot these time scales versus temperature. So in blue and red. So in one case, I plot the Lyapunov exponent. In the other case, I plot the inverse decorrelation time, which is, you know, how soon would you like to forget? So ergodicity, etc. How soon for a fixed resolution, all right? And in the inset, I play the opposite game. I look at a fixed temperature and plot this as a function of the number of degrees of freedom that I have in the system. And you essentially, you know, come up with the same sort of situation. But the point is that, again, intuitively, it seems a good idea to proceed with, right? I mean, the decorrelation time really should tell you the time at which you forget things. And the inverse of that should really be a measure of the Lyapunov exponent. But the fact that, you know, I haven't fudged things very badly to make the data collapse. I think I had to boost the decorrelation time by a factor of 1.01 or something just to, you know, make the data more presentable. But the fact that they're really of the same order seems to, you know, requires a little more rigorous thought in trying to sort of analyze this autocorrelation function a little better. And, you know, we are hoping that we would be able to sort of do this and then sort of connect it a little with, you know, get a certain completeness to this picture. So at this stage, you know, I should really point out that the interesting universality about this is that Thomas, Shubro, and Roderick in a recent PRL for spin liquids did see a similar square root T scaling. I think there was a correction to that, but something close to that. So there seems to be an underlying universality in which, you know, a spin system, you know, discrete model, etc., and how finite dimensional sort of equations of hydrodynamics, really partial differential equations, which we, you know, when we solve on the computer, we generally sort of course, we make it finite dimensional in a suitable way, seems to, I mean, there seems to be a certain universality to that. I mean, I wouldn't like to claim more than that, but I mean, these are the issues we are struggling with, which is why you see that it's in preparation in some sense. I mean, at the level of burgers, everything seemed to be nicely settled in our heads. But with the 3D Euler, we seem to sort of want to look at this a little more carefully. So essentially, you know, I'm sort of done, but just to highlight that, you know, in this direction, there are lots of approaches we are taking. Again, this harks back to the slide that I said, why is this problem important, or at least why we think it's important. It may not be important to anyone else. So just like, you know, trying to look at an elephant. So with Sugan and Shubro, we are now looking at spin systems with long-range interaction. So early results are interesting. You know, how much of this is destroyed when you move beyond the typical nearest neighbor interaction and you have long-range correlations in the problem. In the hydrodynamic sector, you know, with Vishwanath Shukla, who was Sergey and Mark's postdoc actually, we are looking at the Gross-Pitevsky equation essentially in 2D, especially in light of the anisotropic XXZ results and the transitions across the Kosterlitz-Thouless point. And I believe, you know, there are certain interesting mode coupling results to which we can sort of look at this. On dynamical systems, essentially, we are looking at shell models. There are lots of shell model people here, both in the inviscid limit. I mean, you know, in the regular viscous shell model, you know, beginning with Okitani, Yamada, etc. I mean, this is a solved problem. I'm not claiming to look at something new. But in the inviscid problem, inviscid shell model, there are certain interesting results that I have seen, which I don't understand, so I'm not presenting it here at all. And I would sort of like to see this crossover. I mean, typically, I see signatures of spontaneous stochasticity of the sort that Alexei and others have looked at. But when I go to the inviscid case, there seems to be a crossover. Where is this crossover coming from, etc.? And finally, and this is really speculative, we are trying to adapt certain ideas here to driven dissipative systems, you know, active systems, etc. This is with people who've joined the group just recently, and we are sort of still reading up. But there, I mean, there are things that we see there which I think might make it interesting. So given that I began with temptations and redemptions, and given the discussion session last evening, I just would like to end with an epilogue, which is, you know, which is unashamed advertising. Maybe it will be useful in the next informal discussion session, which is this, you know, recent paper this year, you know, Sugan, my PhD student's work. Of course, Sergey is involved, Uriel is involved. So, you know, I had to sort of honor the chair and the organizer at least. So where we sort of showed that there is a way to numerically obtain weak dissipative solutions from these Galerkin truncated inviscid equations without explicitly putting in viscosity. The key challenge is in the Euler, and hopefully in a year from now, we'll have slightly more interesting results on this front to present in the physical version of this meeting. So yeah, so basically it's 7:45 and I'm supposed to stop. I have a couple of minutes, but I think I can stop here. Yeah. Thank you.
Okay, thanks, Samriddhi, for your very interesting talk.
Yeah.
So,
I should look at the chat box, right?
Yes, there is one in the chat box, only one question at the moment. Are you getting the measure of temperature from the variance of the velocity distribution?
That's right, that's right, yeah.
Okay.
Yeah.
Okay. Who else would like to ask a question?
Rahul Pandit here. May I ask a question?
Sure.
Oh, sorry. Takeshi has one already.
Yeah, Takeshi, thanks for the question. It's something that we are looking at. We don't have an answer to it. I mean, we are, as you can guess from the fact that we started to explore things in the autocorrelation world, we will be sort of looking at but no, I don't have an answer right away. I mean, yeah.
Do you think you are looking at the higher order correction to the FDT, for example?
Yes, in the expansion. So you know, there was an earlier paper by your colleagues, right? You were also part of that work, I guess. And so those are, so that's something that I'm actually, you know, at the end, I talked about the dynamical system. So that's something that I'm playing with in the shell model before I adapt here. But right now, I don't see an obvious theoretical way.
Okay, thank you.
Yeah, I mean, that's why, you know, things are still in the flux with the Euler results. So I'm sorry if I presented things which are slightly speculative. Yeah.
Thank you.
Yeah. Uriel, you had a question.
Yes, you want to hear it?
Well, why not? It's always a pleasure to hear you, Uriel. So.
Yes, all right. So okay, let me switch on the, so that people can see me. Yes, an outrageous question, of course.
Oh dear.
Let me point out that at the moment, the whole world, or most of it, has some strange things. There's rumors of COVID and rumors of vaccines, etc. Now, yes. What I want to point out is that everything seems to go, in a sense, faster than before. The illness is growing faster sometimes, but the vaccine is maybe 3 to 5 years faster than normally, and seems to show some success. Now, to return to these tiger problems, we, not so long ago, we were saying it would take us a number of years until we can seriously touch three-dimensional problem. Isn't it true that maybe we can do things faster and better?
Is that the question, Uriel?
Yes. To everybody, not just to you, of course.
So should I let everybody answer, or do you want me to take a first stab?
Well, maybe you can give us your feeling.
Okay, the feeling is the following, Uriel. By understanding, you mean the analog of our understanding in 1D in terms of thermalization in physical way. So to make a previous statement, I know it's live on YouTube and probably WWF people will hit me. We have seen tigers now, or more precisely, Sugan has in 3D Euler. So I'm very happy to share this. So what we now know is, Uriel, if you can see these wriggles in the net strain, Sugan, it'll soon come up, you'll see these beautiful oscillations, something that Takeshi was the first to look at. Yeah, sorry, Uriel. Something that Takeshi had seen many years ago in the 2D problem. So they proliferate everywhere. So Sugan is working on this a lot, and he's, he knows about this much more than I do. And what we are able to pin down a little without understanding, there's a difference between pinning down and understanding, right? Is where are these wriggles coming from? And why is it that the net strain, the local strain is just a way, it's something that Schumacher, Hamilton, and Dahm had developed, and we sort of used their idea to try and sort of amplify what you see in the global strain thing. So I can certainly tell you that I think the progress will be fast. Whether it will pass phase 3 trials, I cannot guarantee right now, Uriel. But I certainly, and I've worked on these problems with you and Sergey and Takeshi, I certainly do see a certain light at the end of the tunnel in terms of where the hotspots of thermalization in 3D Euler is. Mark had told us what this is in spectral space, but as you know, we were after physical space. What's the analog of what we had seen in Burgers? And I think we are able to pin it down to the strain picture. And I hope that we will have a result which we let other people hit us on the head with in terms of theory. Does that, Uriel, does that vague answer, is that sufficiently vague to convince you?
That is a partial answer, because you are very polite and you want to let your colleagues, including Sergey, add some spice to this.
I'm masking my ignorance and politeness, Uriel. Sergey, you're supposed to answer this now.
Yeah, okay, I'll take this.
Sorry, but I'll wait. Yeah, I'll wait for other questions, because I think there's something from Rahul, right? Sergey, if that's fine with you. Or...
I'll take this opportunity and answer the question with my own question. So, because I have to say, for me, it's new what you are saying about three-dimensional work. It's very nice to hear that, very intriguing. So you said you can pin down the places where your wiggles occur. Okay.
Yeah. I think we are in 2009 or 10 at the stage of our burgers. Do you remember when we were able to pin it down, the triggers of thermalization? So I think
let's actually maybe clarify. I mean, one thing is the cause of the wiggles, which is a sharp gradient in burgers. And another place where the wiggles occur, in burgers, they occurred on a smooth ramp where no sharp gradient is supposed to be.
Yes.
So do you observe something similar? And if so, what is the sharp gradient object in this case?
So the sharp gradient object, again, you know, this is really work in progress, but and COVID doesn't help. The sharp gradient here is we were able to sort of identify a threshold for the net strain in the problem. And then we were able to zoom into that net strain and see, just like in burgers before we had a full understanding, the resonant points seem to be out of the blue. Here again, the tigerish structures that is playing on a loop on your screen seems to come out of the blue. But empirically, I think Sugan, if you give him a snapshot, is now able to tell you without seeing the simulation, like we were able to do it for burgers, you know, Yumi, Takeshi, Uriel, tell you, zoom in there, wait, and you'll see it. And so now the question is understanding why those resonant points are getting picked up.
I have a follow-up question.
Uriel, can I just, sorry, yeah,
Not
okay,
finished,
continue.
of course.
No, all I was saying was if there was any OTOC related question, then we'll postpone this to the Friday informal discussion. Or anyway, Sergey should be able to spot that if it's on the chat box. So Uriel, continue, sorry, yeah.
Yes, one thing that has changed dramatically is that during the time when you had it was difficult for you, Samriddhi, to come to Nice for various reasons, and when Sergey wasn't at all in Nice, etc., not much happened except in fluctuating events that separated by several years. Things are very different now because the modern technology allows us to collaborate without being at the same place.
Yeah.
And what I would like to emphasize is the following. Generally, people try to think about what is sometimes called subgrid scale modeling in an empirical way, which is, for example, how can we, with computers, which are what they are now, get a lot of juice without having to worry about too much dissipation. That, of course, but there can be a number of other questions which may or may not directly be applicable to industrial goals, which are more fundamental. And I would like to point out or ping out, become more aware of the truly fundamental issues that are related to tigers and which questions in turbulence, not just practical, but fundamental ones, can be answered by this kind of research. my feeling is that in the past, there was too much emphasis on practical thing where funding is perhaps easier, etc. But we should think differently now. This is a both political and scientific remark.
Okay. Yeah, I mean, I see your point, Uriel, of course, as you might guess, but yeah.
So, anybody else want to ask a final question? We have a couple of minutes. Okay, well, maybe then, okay, so this is another one on the chat. Can you explain how you are extracting the decorrelation time?
Well, two ways. One can sort of either fit a Gaussian, because theoretically we can calculate the autocorrelation function for the thermalized case. So you can calculate it from fitting the Gaussian, or, and this we've checked, or you sort of measure the time at which it falls to 1/E. So both are self-consistent. Yeah. So you can fit a Gaussian trivially, and or you can do this.